Welcome to AI Paper Slop. We are jumping right in today. The paper is a definition and roadmap for world models, and this is from the physical intelligence team at the Shanghai Artificial Intelligence Laboratory. And the core insight you need right now, right off the bat, is that the term world model has completely lost its meaning.
Yeah, it really has. I mean, it's being slapped on literally everything from, standard model-based RL architectures to video generators like Sora.
Right, and this paper argues that just generating a plausible video does not make a world model. Like, a true physical world model is actually a compression mechanism. It distills the state transition processes of the physical world, and it does it under finite computational resources.
Exactly. And to actually work in reality, it must be omnimodal, handle asynchronous data frequencies, and operate via local observations.
So for today's deep dive into the source material, we are looking at their proposed inverted pyramid data workflow and this Trinity architecture, which is designed to evolve these systems from just passive renderers into active engines for physical AGI.
Because, for anyone listening, whether you're an ML engineer trying to debug a robotic policy, or maybe a researcher training a diffusion model, this shift is huge. I mean, we are looking at a hard pivot from predicting pixels to actually understanding physics.
Right, because if we want autonomous systems that work in the real world, just looking realistic is, well, it's completely insufficient. The model has to understand the actual mechanical and causal rules governing the space.
Yeah, exactly.
So we just established that the current, colloquial definition of a world model is broken. How does this paper actually fix it? Because they fundamentally shift the goalpost from what a model outputs to what a model actually understands.
They do. And they start by contrasting two of the big prevailing views in the field right now. So first you have Fei-Fei Li's functional taxonomy.
Right, where she categorizes world models by what they specifically do inside the agent environment loop. So you have renderers that generate pixels, simulators that predict state transitions, and planners that propose actions.
Which is an incredibly useful breakdown for classifying outputs.
Yeah.
But the Shanghai AI Lab authors argue that it kind of skirts around the core issue, which is what the internal representation actually is. Like it treats the world model as a black box that just spits out a specific modality.
Yeah. And then the counterview to that is Yann LeCun's approach, right? He pushes for joint embedding architectures in latent space.
Right.
Because his take is that pixel-level reconstruction is just this massive waste of representational capacity. I think he calls it focusing on photometric irrelevancies.
Yeah, photometric irrelevancies.
Yeah.
Because LeCun's argument is that predicting every single leaf on a tree in a video is totally useless if all you want to do is, drive a car down the road.
Right, you just need to not hit the tree.
Exactly. He takes it a step further and argues that generating exactly what a scene looks like is inherently flawed for decision-making. And the Shanghai AI Lab team, they partially agree. They state that pixel-perfect reconstruction shouldn't be the ultimate objective.
Though they have a caveat, right?
A huge caveat. They argue reconstruction quality is still an incredibly valuable diagnostic tool. Like it's the best way to trace what vital information your compressed latent representation might be, silently throwing away.
Which leads right into their formal definition. They define a world model as a finite resource approximation of physical state transitions. I mean, the universe has infinite computational power driving its physics. But our engineered systems run on silicon.
Right, they have strict limits.
So they have to use compression to approximate reality. And the authors outline 3 intrinsic properties this approximation must have. So first, an omnimodal work scope. We aren't just talking vision and text anymore.
No, we're talking tactile feedback, audio, proprioception.
Right.
Everything unified in one single latent representation.
Yeah. And the second property is multidimensional asynchronicity, which, that addresses a massive engineering nightmare in robotics.
Oh, it really does. Because different sensors sample the world at vastly different speeds. I mean, a camera might feed you vision at 30 hertz, but a tactile sensor on a robotic gripper is firing at 200 hertz.
And an audio stream could be coming in at 44 kilohertz.
Exactly. So a true world model has to process that multi-frequency asynchronous data smoothly into a coherent state update.
Yeah.
You can't just force everything into a rigid, uniform time step like we usually do.
Right. That just breaks the physics. And the third property they mention is locality. The idea that the agent can only perceive a local region and outside forces act as interventions. This is where they formulate the world as a partially observable Markov decision process, or POMDP.
Yeah, let's break that jargon down for a second. Plain English, it means the AI can't see the whole board of the universe at once. It only sees its immediate surroundings, and it has to infer the rest of the world state from that really limited viewpoint.
So locality means the model has to have object permanence. Like if a ball rolls behind a couch, it leaves the observable state, but it has to remain in the inferred hidden state.
Exactly. And this whole framework represents a really deep philosophical shift in AI. We're moving away from just asking, what will happen next, which is just autoregressive prediction,
Right.
to asking what is happening, why does it happen, and what will happen if I intervene. That requires actual epistemic reasoning. The model has to know what it knows and know what it doesn't know about the physics of the scene.
But I'm hung up on one thing here. Going back to Lacan's latent-only view, if you discard pixels entirely and just work in abstract latents, isn't that super dangerous in a physical environment? Like if you are an ML engineer building a high-precision robotic manipulator, you can't just ignore a tiny set of pixels that represent, say, a thin wire the robot is about to clip.
Yeah, and that is the exact tension the authors highlight. Lossy compression is an unavoidable trade-off in these systems.
Yeah.
If you lean too far into high-level semantic abstraction, you lose the fine-grained physical dynamics.
Right, the perceptual fidelity you need for exactly that scenario, that tiny decision-critical contact point.
It's exactly. So the paper argues the goal isn't just blanket compression, it's targeted information preservation. You have to design the architecture to intentionally discard the nuisance variants. So the shifting shadows, the camera noise, the lens flare.
While fiercely protecting the variables that dictate control and physical contact.
Right.
Okay, so if a true world model is about compressing physical laws rather than just memorizing visual patterns, where does the training data actually come from? Because you can't just scrape Wikipedia text to teach an AI how a glass shatters.
No, you definitely can't.
And proprietary robot data from labs is, well, it's way too small to learn general physics.
It is. The authors put forward a very blunt premise here. Architecture and compute dictate how fast a model learns, but data diversity determines the absolute generalization ceiling.
So you could throw, like, 10,000 H100 GPUs at a model, but if the training data lacks physical diversity, it's just going to fail in novel real-world situations.
Precisely. Proprietary datasets, like exoskeleton sensors or robotic teleoperation logs, they're structurally constrained. They are never going to scale to the magnitude required to learn universal physical priors.
So what's the alternative?
The only viable, scalable source of data is internet video. It gives us hundreds of billions of diverse physical interactions.
Hold on, though. If we apply that to the real world, relying on YouTube or TikTok to learn physics seems completely broken. I mean, the internet is flooded with CGI, cartoons, wildly distorted camera angles, jump cuts. How on earth does a neural network separate true Newtonian physics from a superhero movie or just photometric noise?
So they solve this by introducing what they call the inverted pyramid workflow. It's this three-tier pipeline designed to literally distill physics out of noise.
Okay, how does that work?
Well, at the very top, the widest tier, you have that massive ocean of unstructured web video. It is incredibly noisy, yes. But buried within those billions of pixel streams are foundational latent physical priors.
So things like object permanence, structural rigidity, kinematic limits, how lighting interacts with geometry.
Exactly. The model uses sheer scale to internalize those broad universal rules, even if some of the data is flawed.
But if the top tier is just billions of messy videos, you can't feed that directly into a robotic control policy. You must have to filter or synthesize it somehow to make the movements readable for an agent, right?
Precisely. And that brings you to the middle tier, synthetic and filtered data. Here, you drastically prune the dataset. You use vision language models or heuristics to filter out the CGI, the cartoons, the impassable physics.
Oh, I see.
And use synthesized data to fill in gaps for specific actions. You strip away the irrelevant visual context and standardize the action representations. The pipeline is actively distilling the noise down to retain only physically meaningful motion signals.
Signals that a robot could actually map to its own joints, which naturally leads to the bottom tier, right? Real-world task data.
Right. This is the narrowest point of the funnel. It's highly curated, heavily structured, and fully optimized for embodied fine-tuning.
So it's small enough to be efficient to train on. But because the model has already ingested the top two tiers, it isn't learning physics from scratch.
Exactly. It brings all those broad physical priors from the internet down into the specific real-world robotic task. The world model acts as a compression mechanism designed to shed the cinematic noise and keep the structured causal information.
Wow. And this data workflow dictates how we evaluate the three main architectural paradigms currently dominating the field: which the paper breaks down in a lot of detail.
It does. So first we have observation-level generative models. These are systems like Sora or Genie, and they scale beautifully with that top-tier internet video. Their visual fidelity is staggering.
But the paper says they suffer from compounding prediction errors. Let's unpack the mechanics of why that happens. Like, why does a model like Sora eventually hallucinate a dog just blending into a brick wall?
Because it's predicting directly in a high-dimensional observation space, usually auto-regressively predicting video tokens or patches. It doesn't have an underlying 3D mesh or a rigid body physics engine anchoring its predictions.
So it's just guessing what the next pixel patch should look like based on statistical patterns in its training data.
Exactly. So a tiny error in frame 10 becomes the ground truth for frame 11. Over long horizons, those errors compound exponentially. The system experiences temporal drift because it just has no structural understanding of 3D space to, snap it back to reality.
Got it. Then we have latent-space world models. We're talking about architectures like the Dreamer family or JEPA. These shift away from visual appearance entirely. They map observations into a compressed latent vector and focus solely on task-relevant state evolution.
Right. And these are highly computationally efficient for imagination, meaning planning out long sequences of actions entirely within the latent space without ever rendering a single pixel.
Because the representation is so compact, they scale beautifully for long horizon planning.
They do. But going back to our earlier point about the wire, they face the severe risk of objective mismatch. By abstracting so aggressively, they discard visually minute details that are absolutely essential for physical task.
Which brings us to the third paradigm. 3D enhanced or object-centric models. So this includes neural radiance fields, or NeurFs, 3D Gaussian splatting, and occupancy networks.
Yeah, and for the ML engineers listening, Gaussian splatting represents 3D space not as a rigid polygon mesh, but as millions of continuous, fuzzy mathematical blobs.
Right, which makes the scene differentiable, giving you a spatially queryable structure. It solves the object permanence issue beautifully because the geometry is literally baked in.
It does, but the mechanism has its own severe limitations. These 3D-centric models struggle immensely with dynamic, rapidly changing scenes. Updating millions of Gaussian splats in real time as a robot manipulates, say, a deformable object like a cloth is computationally brutal.
And they often require highly structured multi-view supervision to train effectively, right? Which you don't typically get from a single camera YouTube video.
Yeah.
So if I'm building an autonomous driving system today and I'm staring at these three paradigms, what do I choose? Do I use a latent model for millisecond inference speed and long horizon planning? Or do I use a 3D occupancy network to ensure spatial accuracy so my car doesn't merge into a concrete barrier?
The paper's conclusion is that forcing ML engineers to make that choice is a failure of current architectures. The immediate frontier is cross-paradigm unification.
So an omnimodal world model.
Exactly. You need an architecture that combines the generative, data-absorbing scale of observation-level models, the computational efficiency of latent space models, and the grounded spatial consistency of 3D models. The field is rapidly moving towards shared architectures, where a single, unified model can act as a renderer, a simulator, or a planner, depending entirely on how you query its latent space.
Okay, let's assume you achieve this architectural marvel. You've trained it on the inverted pyramid, and it synthesizes all three paradigms. How does an autonomous agent actually use it to make a decision? Because this brings us into the mechanics of model-based reinforcement learning, or MBRL.
Right. So in a traditional MBRL loop, the agent interacts with the environment, stores that data in a replay buffer, and uses it to learn an approximate transition function, which is the world model. Then it exploits that world model as a cheap, differentiable surrogate for reality.
Oh, I see. So instead of breaking a $2 million humanoid robot by failing a task in a physical lab, the agent tests millions of potential policies inside its own imagined world.
Exactly. But the authors highlight three major failure modes when you try to execute this in practice. We already touched on compounding error, where tiny inaccuracies grow superlinearly in deep rollouts until the imagined state is just nonsense.
Right. And the second is objective mismatch. You might be explicitly training the world model to minimize pixel reconstruction loss, but what you actually need for the policy is to maximize the expected return.
Yeah, optimizing for pixels does not automatically yield a good control policy.
But the third failure mode is the one I find most fascinating. The optimism-pessimism bias. I mean, think about the mechanical relationship here. A planner is essentially an adversarial consumer of its own world model.
That's a great way to put it. The planner's sole job is to search for action sequences that yield the highest predicted reward. Therefore, if the world model has a flaw, like an optimistic error, where it mathematically predicts a massive reward for a physically impossible action, the planner will inevitably discover and exploit it.
The planner will literally hallucinate value in regions of the latent space where the model's grasp on physics is fundamentally broken.
It will. And to fix this hallucination problem, the authors introduced a concept called chain of imagination, or co-II.
To understand this, let's step away from AI for a second and think about an expert billiards player visualizing a complex trick shot. They don't just look at the table, they perform what the paper calls abduction, action, prediction.
That is a perfect analogy. Abduction is the billiards player looking at the table and inferring the hidden variables.
Yeah.
They assess the friction of the celt, the weight of the cue ball, the exact angle of the rail. They abduce the latent state of the physical system.
And then action. They imagine the surgical intervention, striking the cue ball with backspin at a 45-degree angle.
And finally, prediction. They mentally roll forward the simulation. They simulate the ricochets, the energy transfer, all while holding the background context, the table itself, constant.
And chain of imagination brings this exact process to AI. It fuses the sequential reasoning of LLM-style chain of thought with counterfactual physical dynamics. It is causal reasoning applied directly to physical simulation.
Yeah, exactly.
But I keep coming back to the hallucination issue. I mean, even an expert billiards player might visualize a shot that defies the laws of physics if they misjudge the spin, right? What stops the chain of imagination model from feeling optimistic and hallucinating a winning robotic manipulation that simply cannot happen in the real world?
And that vulnerability is exactly why the paper strongly calls for physics-informed learning and constraints. You just cannot rely purely on data-driven statistical likelihoods when dealing with the physical world.
You have to mechanically inject physical structure. Things like differential equations, conservation of mass and energy, contact constraints directly into the learning process or the loss function.
Exactly. The model shouldn't just generate a future state that looks statistically plausible based on internet videos. It must generate a future that is physically admissible. By constraining the latent variables to obey these laws, you mathematically prevent the planner from hallucinating a shortcut that violates physics.
Which brings us to the ultimate roadmap. I mean, we've dissected the pitfalls of correct models, the noise in the data, the compounding errors, the adversarial planners. To close out today's deep dive, let's look at the concrete roadmap the Shanghai AI Lab proposes for achieving physical AGI. The holy grail they propose is encapsulated in this phrase: one state, many decoders.
It is a profoundly elegant concept. Historically, we build separate bespoke models for separate tasks. A vision model for perception, a physics engine for simulation, a policy network for action.
But one state, many decoders, proposes a single, unified physical representation. It's intrinsically compact, heavily grounded in simulation, and geometry adaptive.
Right. From this single shared latent state, you can decode into whatever modality you require at that exact millisecond. If you need visual feedback, you decode it as a renderer. If you need to calculate physical stress on a robotic joint, you decode it as a simulator. If you need affordances to choose an action, you decode it as a planner.
The engineering implications of that are staggering. A single latent space mathematically capable of outputting a photorealistic video frame and a rigid body physics calculation simultaneously. We are seeing very early primitive precursors to this, like Gaussian.
Yeah, which attempts to drive both kinematic simulation and visual rendering from the exact same point cloud representation. But scaling that to a foundational level is, well, it's the defining engineering challenge of the decade. And to get there, the paper proposes a Trinity architecture for autonomous evolution.
Let's mechanically break down this Trinity. So component one is the world model. Its function is to imagine scenarios, propose novel tasks, and maintain the overarching belief state about physics.
Right. Component two is the agent. The agent actually executes the policies either within high-fidelity digital twins or embodied in a real-world robot.
And component three is the evaluator. This is the critical feedback loop. The evaluator assesses the outcomes of the agent's actions, diagnoses failures, measures the actual friction and sensory noise of reality, and feeds all that data back to update the world model.
It creates a relentless, closed-loop cycle. The system is no longer just passively watching billions of YouTube videos. It is actively proposing physical tasks, executing them, evaluating where reality diverged from its imagination, and updating its internal equations of physics.
It learns through physical trial, error, and imagination, mirroring the developmental stages of biological intelligence.
Yeah, exactly. The paper also touches on two critical, often ignored infrastructure issues here: privacy and sustainability. Gathering high-quality physical data often involves proprietary lab environments or, sensitive domestic spaces. So they propose federated world models.
Oh, right. Where entities can train locally and share only the latent gradients to update a global foundational world model.
Yeah,
That way, they never expose their confidential, localized video data.
exactly.
And their point on sustainability is something every ML engineer needs to internalize. Because right now, the entire industry obsesses over inference costs, FLOPs, and GPU utilization metrics. But the paper insists we have to measure the full life cycle carbon footprint of physical AI systems.
Because when you transition from digital LLMs to physical AGI, the carbon math changes entirely. You aren't just measuring the power draw of an H100 cluster anymore. You have to account for the polymer synthesis required to manufacture millions of robotic actuators.
You have to measure the rare earth mining required for the physical servos and batteries. Optimizing a model's compute efficiency is a fundamentally incomplete metric if we ignore the massive embodied carbon cost of the physical hardware interacting with that model.
It really is.
So, what is the ultimate takeaway for you, the technical listener? The mandate from this paper is crystal clear. Stop building video generators and labeling them world models. Stop trying to merely predict pixels autoregressively. You have to start engineering unified compression mechanisms dedicated to physical state transitions.
Yeah. Your focus has to shift toward targeted information preservation and enforcing rigid physical constraints within your latent spaces. If you are an ML researcher or engineer working in embodied AI, your primary metric of success can no longer just be visual fidelity or FID scores.
The true test is whether your model's internal representation is structurally robust enough to support reliable, long-horizon decision-making in a chaotic physical environment. Well, I want to leave you with one final, deeply philosophical thought from the paper's section on scientific discovery. The authors emphasize that these world models extend far beyond just robotics or autonomous driving. They apply directly to chemistry, biology, and astronomy. Imagine a scientific world model that doesn't just predict the next frame of a drone video, but perfectly simulates and hypothesizes molecular reactions entirely within its latent space.
Yeah, think about it. It abduces the state of a novel chemical compound. It imagines a surgical intervention may be introducing a new catalyst. It perfectly simulates the binding affinity and the resulting reaction.
It evaluates the outcome, scores it, and instantly updates its own physical beliefs. It executes this loop millions of times a second. If an AI can autonomously hypothesize, simulate, execute, and evaluate novel physics within its own Trinity architecture, well, at what point does the AI stop being a mere tool for the human scientist and simply become the scientist itself?
It's a wild thought. At that point, the physical world we live in is reduced to nothing more than the AI's own personal, occasional evaluation loop to double-check its math.
Let that sink in. Keep iterating, and we'll see you next time on AI Paper Slop.